welcome to this technical walkthrough of my time series anomaly detection project. The objective of the system is to identify catastrophic failures in highly complex noise environments, much like reading hundreds of interconnected telemetry sensors on a NASA spacecraft. Supervised learning fails here because true anomalies are so rare you don't have enough label data to train on. My solution uses generative deep learning, specifically a mathematical architecture called a variational autoencoder. It learns entirely unsupervised. By feeding it hundreds and thousands of normal telemetry readings, the neural network learns a mathematical probability of what normal behavior is. If a sensor suddenly deviates, the model fails to reconstruct the timeline and throws a massive mathematical error, instantly flagging the anomaly. Before looking at the PyTorch logic, let's look at how I engineered the pipeline for reproducibility. Right now, you are looking at my environmental hyperparameters. Instead of hard coding values deep in my script, I map variables like sequence length, latent dimension, and batch size here so the algorithm can be safely tweaked. I wrap the entire machine learning process inside a Docker container. Looking at my Docker Composer file, notice how I mount local volumes for data and results folder because of this architecture. Someone can pull my code, run a single command safely inside a containerized sandbox, and have the trained models and the metrics seamlessly sync right back into their local folder. I wrote the let's trace how the data flows. So in data loader.py, I stimulate continuous multidimensional proxy streams, but neural networks don't naturally understand the time. So I have written this create sequences function to solve this. It applies a sliding window instead of looking at solitary timestamps. This logic slices the data into overlapping sequence chunks of 50 steps. This generates three-dimensional tensors matching the shape of batch, sequence, and the features. Crucially, right above that, I use a scikit-learn min-max scalar. Notice how I only apply the fit transform to the training data and strictly transform on the test data. This guarantees the absolute zero data leakage while validating our anomalies. Now let's examine the PyTorch architecture in model.py. A standard autoencoder just crushes data into a bottleneck, but my LSTM encoder here relies on recurrent long short-term memory layers to actually compute the sequence. Notice lines 15 and 16, the final hidden state splits into two fully connected layers, FCMU and FC log VR. Instead of a fixed point, the model learns a mean and a variance. To make this differentiable during backpropagation, I implemented the reparameterization trick. Right here, sampling standard noise alongside our variance to generate a smooth probabilistic latent space. And just below this is the semi-supervised variant, the conditional variational autoencoder. See right here where I used one hot encoder. I literally mathematically concatenate known Boolean labels directly into the PyTorch tensor because it enters the LSTM. If the system knows what a rare anomaly looks like, pending that condition acts as a superpower, forcing the model to draw sharper discrimination boundaries. Looking at the main.py, you can see it's cleanly orchestrates the sequence, pre-process, train, and evaluate. Now let's evaluate this live right now. As Docker initializes the pipeline, it's booting the Python environment and calculating the loss dynamically over the 20 approaches. Notice, like, notice the terminal logs. Right now, the training loop continuously calculates the LBO loss function, combining mean squared error against the KL divergence. The loss is strictly falling, proving the model is fundamentally learning the mathematical physics of our normal spacecraft engine sensors. It just finished the unsupervised loop and is now rapidly optimizing our semi-supervised variational autoencoders. The container just transition to step 3 evaluation. Remember the model predicts anomalies through high reconstruction errors, but how high is too high? In evaluate.py, my calculate threshold function dynamically sets an absolute limit precisely at a 95th mathematical percentile of the error spread. Here in the results folder, you can see the metrics and you can see the semi-supervised metrics JSON and also unsupervised metrics.json. The terminal has successfully exited by looking at the JSON dumps my pipeline just created locally, so you can see the comparative performance because it utilized the conditional features. My semi-supervised F1 outperformed the purely unsupervised model. Now let's have a look at the plot. To visually prove this, look at the output plot generated by the code. The solid blue line tracks the model's mean squared error prediction. The faint red vertical bars represent the ground truth hidden anomalies. Notice how every single time the blue line dramatically spikes, it aligns flawlessly inside a red zone. The model correctly triangulated the anomaly blindly. That concludes the workflow spanning the generator sequential distribution to container deployment. Thank you so much for watching.